I want to use this opportunity, I think, to take a little bit of a step back from the stuff that we normally do in XAI and address some of the more philosophical questions. So on a probably very naive model of scientific progress, we start out in philosophy figuring out what the questions are. Then we go to science and we find the answers to those questions, and then we do technology on top of that. And one of the things that I really like about XAI is that you get a little bit of all three of those things. That said, I think it's fair to say that the majority of work is on the technical side of things. And I guess what I'm going to be saying between the lines here in this talk is that I still think there's room to do some philosophy in XAI. And I'm also going to suggest, I think, that in doing so, we could reach out to the philosophers. Over the last half a year or so, I've been reading a lot of philosophy papers and talking to a lot of philosophers about XAI, and I think there's less of a bridge than there ought to be. If you go to some of the best philosophy journals out there, there's a lot of stuff on. There's a bit of a delay here. There's a lot of work on AI, and there's a lot of work on XAI. But there's also, I think, a feeling among a lot of philosophers that they're not really having a conversation with us. Two of the philosophers that I've talked to over the last couple of months, superstar philosophers of language, Kaplan and Dever, did a book in this year where they complain about how researchers in AI see them as lunchtime entertainment at best. And kind of wearing my AI hat, I don't blame AI researchers. There's a big gap here. People speak different languages, and there's also reading a lot of these articles, just a lot of false assumptions being made about the technology, et cetera. But I still think that there's a reason to have this conversation, and that we could learn a lot from philosophers. So that said, I'm going to get started. I want to start with, here we go. Okay. I want to start with some very high-level observations about deep neural networks and kind of what it means to be a black box. So the standard view of things would be something like this, I think. Deep neural networks are black boxes in need of explanations. So this certainly, to me, sounds like the opening sentence of a fact or ACL paper on XAI. And I don't want to say here that that statement is false, because I think that would depend on how you define black boxes and explanations. But what I want to say is that, to me, the sentence on the right, that deep neural networks are white boxes and explanations, kind of resonates as well. And I think in many ways I would prefer reading that as the opening sentence in a paper on XAI. So let me explain what I mean here. So in a very trivial sense, deep neural networks are white boxes, right? In the sense that there's nothing secret going on. There's nothing that's really hidden. You can print out all the weights. You can print out all the computations. And as such, they're white boxes or transparent. They're just very big white boxes. As for explanations, if you go to the philosophical literature on explanations, you'll see a lot of different definitions of explanations. But one of them that I really like, and which is very common, is, for example, by Kenneth Craig in his book, The Nature of Explanation, where he talks about an explanation as something that enables you to predict a phenomenon, and with the additional constraint that it has to generalize well. I mean, that's exactly what deep neural networks are for. They provide us with predictions and generalizations if they work. So in that sense, a deep neural network already explains why, in terms of X, now the explanation may, of course, be false. It may fail to generalize properly, and it might be overwhelming. It might be a very long explanation. It might be a very complex explanation, and for that reason, it may be useless for some purposes, for example, teaching or popular textbooks or so. But I still think that perspective is interesting to keep in mind. I really think the black box metaphor is unfortunate because it's binarizing something that shouldn't be binarized. Because deep neural networks are certainly more informative, for example, than the kind of black boxes that you have in educational settings where, you put this black box on the desk and there's some tubes in, some tubes out, and you pour liquids in and you see what comes out to give students a chance to infer stuff about what's happening inside the black box. Deep neural networks are way more informative than that. So I would prefer terms like, overwhelming or hard to summarize in a few words for deep neural networks. But I'm going to settle on opacity here because at least that has that, it refers to something continuous. Now, I also want to say that I think there's at least two kinds of opacity that we need to distinguish. There's the opacity of why neural networks predict what they do given the input data. That's what most people in XAI tend to talk about. And a lot of what we've talked about what we talked about this week, there's another sense, which is the opacity of how neural networks settle on the functions they settle on given the training data. So I'm going to refer to the first one as inference opacity and the second as training opacity. So this is the kind of thing that influence functions, for example, is for. I think similar distinctions have been made in the literature. I also think it's interesting to think at this very high level about where the opacity is coming from. And if you go to the literature, there's a lot of contenders out there. So one is, of course, the number of parameters. So you'll find statements like it's generally difficult to interpret or explain how or why a deep learning algorithm arrives at a particular decision, given that they're built on numerous hidden layers and millions of neurons, which makes them opaque. So opacity here stemming from the number of neurons. You'll also find statements like deep neural networks exhibit nonlinear structure, which makes them opaque. So attributing the opacity to nonlinearity. Some people blame continuity. Discrete representations have the advantage of being readily interpretable, unlike continuous representations. Some people blame lack of grounding, and others blame lost training history or the fact that things are incremental during training. And there's many ways to think about this. One is in terms of sufficient conditions. So from that perspective, I think it should be relatively clear that at least for inference opacity, the only contender here that's a sufficient condition for opacity would be the number of parameters. And it's sufficient because like even a naive Bayes model would be opaque with enough parameters. But also if you go through the other alternatives here, nonlinearities, for example, I mean, clearly decision trees are thought of as inherently interpretable, suggesting that nonlinearity is not a sufficient condition. We reason a lot in continuous space in geometry or statistics, suggesting that continuity is not a sufficient condition. Lack of grounding, momentum is the product of mass and velocity, and mass itself is the product of volume and density. So we have all these non-grounded concepts that we can reason with. But it seems like the number of parameters is more of a sufficient condition for inference opacity. Now, for training opacity, there's this fact that we tend to toss out the training history, and that our models, the final status of our models, depend very heavily on the order in which they would see training data. So I think for training opacity, there's at least two sufficient conditions: the number of parameters as well as the lost training history. And I think those kind of I think thinking about these things will inform the kind of practical work we want to do in XAI. And I think in summary here, the kind of view that at least I have when doing work in XAI is, if deep neural networks are these white box explanations, just very large, that kind of suggests that XAI is a summarization problem with an abstractiveness, faithfulness trade-off. And I mean, this is not super surprising. There's a lot of methods that align really well with that, like knowledge distillation, for example. But it also suggests, because this is sort of equivalent with a bias variance trade-off, that we can bring in a lot of learning theory for XAI, which is nice. So I guess the way I see things, I think of XAI as something that's continuous and instrumentalist, providing explanations at different granularities. And of course, sometimes some of these explanations will have a particular value or function. If you think of, predicting that something is water, obviously H2O is a really good predictor of that. In reality, unless we're talking purified water, samples will contain a lot more, and sometimes you want to know about that, and sometimes you don't. But in general, this will depend on the context and the application. Okay, so that's sort of very briefly, I guess, my high-level thoughts on that, and I now want to talk a bit about why XAI is relevant for science, or if it's still, from this perspective, relevant for science. We've seen a lot of applications of XAI to science this week, suggesting that it is really relevant. But there's actually a discussion about this in philosophy of science, with some philosophers being very excited about XAI, saying this gives us unique opportunities in science. But also philosophers of science claiming that XAI doesn't buy us anything. So I want to take a shot at that discussion, I think. I certainly think that the perspective that I'm suggesting here as an alternative or kind of framing of XAI would lead to a change of how we talk about XAI in the context of science. So just for the fun of it, I brought this abstract that is from a paper I read some weeks ago on XAI for science. And it starts saying, models developed using machine learning are increasingly prevalent in scientific research. At the same time, these models are notoriously opaque. Explainable AI aims to mitigate the impact of opacity by rendering opaque models transparent. More than being just a solution to a problem, however, explainable AI can also play an invaluable role in scientific exploration. So I think the way that I would write that with this alternative perspective in mind, or a way of thinking about XAI, would be something like models developed using machine learning provide potential explanations in scientific research. Explainable AI aims to summarize these often overwhelmingly complex explanations. And more than being just a solution to a problem, however, explainable AI can also play a role in scientific exploration. And I've removed invaluable here because I think on this perspective, XAI shouldn't lead to unique epistemic opportunities, but to something or to opportunities that could also be obtained otherwise. But I'll get back to that. Okay, so but I do agree with the authors here that XAI is useful for extracting hypotheses, and of course, as we've heard about this week, the XAI methods can also be used to verify that our models are right for the right reasons. I'll talk a bit about both here. And again, there's these two types of opacity. There's inference opacity. The kind of methods that we would use here would be things like saliency maps, for example, and can put in any kind of strategy from that family here. These would typically give us explanations that are distributions of our input features, reflecting some local linear approximation, unless you do what Oliver just talked about. And I'm not going to talk about higher order explanations here, but we can talk about in the Q&A maybe. I do want to say, though, that these methods have low recall. What I mean exactly by that, I'll get back to, but this low recall with respect to retrieving relevant scientific hypotheses. Influence functions, in contrast, or other methods for mitigating training opacity will give us distributions over the training data. These tend to have low precision because they're sensitive to initialization. Sorry about that. So basically, in order to use those methods to tell you anything about the training data, you need to marginalize over that. So do averages over multiple runs. So they're slightly different, and I'll talk a bit about both because I want to say stuff about evaluation also, and there, at least they're super different. So as for the low recall of post hoc methods for feature attribution, I brought this one example. So this is an image of a cup. Now imagine a classifier classifying this as a morning image. And imagine that this classifier is binary, so it distinguishes between morning images and evening images. Now, you can imagine a couple of scenarios where this classifier would get this right, assuming that this is a morning image. So in one scenario, it could go with the corners of this cup. And the configuration of the four corners would be sort of the giveaway, something that it had seen with other cups in the training data. Now, most first-order post-hoc XAI methods would not be able to give us that hypothesis, that explanation, because they don't explain in terms of configurations of features, right? So they would have four independent possible explanations, but they wouldn't be able to link them up. Now, in another scenario, the model could get this right by considering the average pixel value. So the light in this image might be a giveaway that this is morning and not evening, for example. Now, post-hoc XAI methods, or most of them, wouldn't be able to give us that explanation either, because they can't explain in terms of accumulated statistics. You can also imagine a third scenario where the model is getting this right because it's realizing that the image doesn't contain any star-shaped objects. So imagine a training set where all the evening images, for example, contain star-shaped objects. The model wouldn't, or like the post-hoc XAI methods that are the most common ones, wouldn't be able to give us that either, right? Because they don't explain in terms of the absence of input features, only in terms of their presence. And of course, any combination of A to C would also be beyond the reach of most methods. So that's what I mean by low recall, and what it means is just that we have to be careful relying too much on these methods for extracting hypotheses, because there's a bias here. Now, as we've heard throughout the week, these methods can also be used for figuring out whether our models are picking up on the right factors in the input. I have a picture of Alvin here, which is kind of my favorite example in the space of a kind of clever Hans type phenomena, citing Klaus's talk. Maybe you're familiar with the story, but this is from Dean Pomelo's technical report on Alvin, where he talks about how they were. So the car here is it's got a camera. It's connected to a neural network that's controlling the steering, and they were driving this car out in a forest. It's a small kind of dirt road with a ditch along the left side of the road, and the guy's driving, and at some point the neural network takes over, and it's going really well. And then they return for lunch, and they're like, let's get the neural network to drive us home, and it just goes crazy. And they come home to the lab, and they realize that what happened is that all the neural network learned was basically staying on the right-hand side of the ditch. And as they turned around, of course, that information wasn't there anymore. So this is just another example of sort of a clever Hans phenomenon. And of course, XAI methods, by comparing the rationales that we can extract with XAI methods with human rationales, that can tell us something about how whether our models are picking up on the right phenomena, which basically means it gives us a window on how robust they will be. But notice that there's a data bottleneck here, that we need the human rationales to be able to do that. And I'll get back to some of the problems in getting that data. But as a bit of a cliffhanger, I do want to say that, and this is work with Oliver also, we're looking into whether there's cheaper ways of getting that data, for example, from gaze or eye tracking data, getting the kind of data that you have in, for example, the eraser benchmark is super expensive, but it's now pretty cheap to get gaze data. And it seems so far that the gaze data is inducing similar method and model rankings as the rationale annotations. we think that would be a really exciting finding if that holds true. Okay, so returning a bit to philosophy of science, there was this debate between people arguing that the combination of deep neural networks and XAI possesses these unique epistemic qualities, or gives us unique epistemic opportunities, and then more skeptical philosophers of science arguing that that XAI doesn't really buy us anything. This is not just Cynthia Rudin. This would also be Emily Sullivan, for example, and to some extent Kaplan and Dever. So I think where I end up in this discussion is something like, if DNNs and DNNs plus XAIs can be more or less wrong explanations, it seems that XAI can help us identify relevant hypotheses, but they're not like the only methods for doing that. Subspace pruning or feature selection techniques, and there are other methods that could get us a lot, get us some of the way. XAI can estimate robustness if the ground truth rationale is available, and I'll get to some of the problems there. So DNNs plus XAI doesn't give us unique epistemic opportunities. I think that's just a false statement, because I think anything you can get out with other means, but doesn't mean as such that XAI is not useful in getting us to interesting hypotheses in the context of science. So I guess where I end up here is a middle of the road type position that falls out naturally of this way of thinking about XAI. Another debate that I recently learned about, and that I think is sort of interesting, and it relates to this distinction between the two types of opacity, is between so-called internalists and externalists. So in most philosophers looking at XAI from the outside would call the activity in XAI internalist, because we're trying to figure out what's going on inside deep neural networks by looking at the internal representations. This is sort of in contrast with how philosophers have approached meaning in humans in the 20th century, where they've argued that, well, meanings are not as such in the heads of human beings, but something that arises out of their interactions with external factors, or the context that they're communicating in. So this is established through external causal chains. Now you can imagine sort of two kinds of externalist approaches to XAI. One, which would be kind of like what people do in philosophy, it'd be conservative in the sense that it would only explain model decisions in terms of past interactions with external factors. But you can also imagine a more progressive externalist approach, which would also allow for future interactions. And so then examples would be influence functions, for example, which are explaining the model decisions through the model's interactions with training data in the past. But you could also imagine a more progressive type of explanation in terms of interactions, like uptraining or LIME, where you are kind of free to use new data to probe the model, but without looking at the internal representations. And this is the distinction here. And this is a real debate in philosophy. I think sort of my take on this would be that conservative externalism is just not going to cut it, because models are not fully determined by the training data. And this is the problem of marginalizing over random initialization, but there's also an interaction with inductive bias. So that I think is too restrictive. I also think that, and maybe this is more interesting for the philosophers, but it becomes clear from the technical literature in XAI that internalism and progressive externalism form a continuum, because you can often probe the relevant representational differences. But anyways, I'm just highlighting this because I think it's a really interesting kind of debate that I wasn't aware of, and I think a nice chance to get the collaboration going with philosophers. I do want to talk some more about evaluation of XAI methods. So we've seen a lot of examples of this this week, and I've talked a little bit about this already. So the common evaluation strategies or heuristic evaluation. I think Oliver had some examples. There's human annotation that we talked about already. And then there's human in the loop type experiments like forward prediction. We have worked on that in our group, and I think this is a really interesting space. The idea here is that, so in the simplest forward prediction experiments, and I think the first ones were in sentiment analysis, what you would do is you would give people the explanations or the rationales of a model, and you would have people guess at what the model would predict on the input example in question. People would do this for sentiment analysis. So they would read a review, for example, and then you would have a highlighting of some words, and they would be the rationales, and you were supposed to figure out whether the model was predicting positive or negative polarity, for example. Now, the problem with that was that when people read a review, they already have formed an opinion about whether it's positive or negative. And of course, there's a belief bias happening here. So in the reverse Turing test, we suggested that instead, what you would do, or what you ought to do, is have a training phase and then mask the task. So people would get a lot of examples of rationales and some labels, zeros and ones, basically, and they wouldn't know what the task was. And then after a while, after some training, you could do the experiment. But I think this highlights an important problem with using human annotation, which is that the human annotations are annotations of what the human rationales are, and you're mostly interested in the machine rationales. So when you evaluate your XAI methods, at least that's what you're interested in. If you evaluate whether your model is right for the right reasons, that's a different story. So there you could use human annotations. Kind of a fourth line of work here is doing real life experiments. Jordan Boyd-Graber has some really cool work in the context of Quizball. We did some stuff on reliability estimation with journalists. So the idea here is that you give people who actually, on a day-to-day basis, sit down and do reliability estimation, you give them tools, right? So in this case, you give them a model and you give them the model's predictions, you give them confidence estimates, and then on top of that, you give them explanations, and you see whether it actually helps people or not. So that's a fourth evaluation strategy, and I think more analytically getting at the inherent limitations of methods is a fourth one. But notice that this is all mostly for feature attribution. And so for training opacity, there's much less work. There's some heuristics that I think have been mostly refuted. And there's no human annotations for influence functions. So Jordan Boyd-Graber includes influence functions in his Quizball experiments, and I think those are great. We're looking into, and I'd love to hear your thoughts on this, we're looking into sort of whether it's possible to have human annotations for training data influence. So the kind of experiments that we're running, we're doing this in different modalities, but I'm getting illustrated with just a math example here. We're giving people examples like, here's a list of X and Y values. So we're saying, if f on 3 is 3 and f on 4 is 5 and f on 5 is 6, what is f on 6? And then we ask participants to, once they give us their prediction, also tell us what data points they find most influential for deciding on the value of f on 6 in this case. And it turns out that people are largely in agreement here, and if they predict the same value for f on 6, they're also going to point to the same numbers. And you can do similar stuff with language examples and image examples and sound examples, and we're trying to see if we can use those kind of annotations to give us rankings over models in terms of robustness, basically. But highlighting this mostly to say there's a gap here in the literature. And this kind of leads me to the final section of what I wanted to talk about here. So if we want to use XAI models to tell us whether our models are right for the right reasons or not, we need data. And as I said, that induces this data bottleneck. But there's an assumption very often in the literature that what's sort of an explanation for one person is also going to be an explanation for another. And I think this is another example of where we might want to take a step back and think a little bit about that. So there's an obvious sense in which different stakeholders need different explanations. So influence functions, for example, may be useful for developers and regulators, but probably not for other stakeholders that can't really manipulate the training data anyways. Scientists may be willing to consider more uncertain associations than affected parties typically would, because they're interested in finding good hypotheses, and that's already a needle in a haystack type problem. But that's not what I want to talk about here. I'm more interested in whether, when evaluating whether models are right for the right reasons, whether that's subjective or objective. And we've started to do some work in this space, basically asking people of different demographics for different rationales for different tasks. In this case, these plots are for sentiment analysis. We're also doing this for question answering, where we see quite statistically significant differences between the rationales that we get for different groups. And we see that model rationales often align better with some groups over others in ways that actually are strikingly similar to the kind of biases that we've seen in language models. For example, when we probe what the language of what groups, demographic groups, language models tend to align with. So I think there's interesting biases also at the level of explanations. And I think that points to another assumption that I think to some extent is maybe this is obvious to people in this room, but there's often an assumption that we can study things like explainability, fairness, and privacy and multilinguality in isolation. So last year at ACL, we had a paper where we talk about this as the square one bias. The hypothesis here is that there's a kind of a prototypical experiment, at least in NLP, where typically you use supervised learning, English data, standard metrics. You don't consider domain shift. You don't consider fairness and efficiency, et cetera. You just get your accuracy scores. And then in research papers, of course, we want to depart a little from that kind of textbook type experiment. So we get interested in fairness, for example, or we get interested in interpretability, and we consider one of those dimensions. So we kind of walk one of the axes in this sort of manifold, but only in one direction. And that makes sense if all of these things are independent of each other, but we kind of know that they're not. So we at least know that fairness and privacy, for example, are at odds. And it's pretty easy to show that interpretability for some definitions of interpretability, that's also at odds with privacy. And it seems empirically that there are all these interactions. And so what we're highlighting is that in the literature, those interactions are not explored very often. And so, for example, in the XAI papers, so we did the survey of ACL 2021 papers, and none of them, for example, looked at fairness and bias. And I think the fact that people provide different rationales, I think, suggests that biases can creep in here too. Also, most work on interpretability in NLP considers English only, and I think that's another type of bias that could creep into that literature. So just to give you two examples of this type of work, we had a paper at Black Box NLP in 2022 where we showed that multilingual models are not equally right for the right reasons across languages. And we got a AI stats paper, hopefully, where we show that interpretability and fairness are often at odds, and that interpretability and privacy are also often at odds. So just some examples of this kind of multidimensional exploration of the research manifold, so to speak. Finally, I just want to mention, if there's a few more minutes, this last research that we're also that we've also been working on, where we've sent a lot of people questionnaires with thought experiments to figure out whether to sort of probe the connection between explainability and trust, because I mean that's one of the common motivations for looking at XAI. And we found these really curious results where, first of all, XAI often lowers trust in different scenarios. There's like a doctor scenario and a job applicant type scenario, where and I think what that's telling us is just that trust is very much a default position for a lot of humans, even when they engage with technology. So that sort of just raises the bar a little for XAI work. But also that perceived trust is higher. So when you ask people in sort of a Bayesian truth serum style fashion, whether they think other people will have trust to a technology in a particular context, they tend to think that other people are more likely to trust the technology than they would themselves. So I think that's also another asymmetry that and again, I'm just putting these things out there because I think these are interesting things to think about for the XAI community. And another reason to once in a while take a step back and spend a little more time on the philosophical side of things. Right. I hope I'm leaving enough time for questions here.